Welcome to the Unit 2 Test Correction Remediation video. This is the guided practice, so I'll work through several samples and then you can complete the independent practice on your own. The first one, talking about heat and temperature, and we're going to make a conversion. For the sake of simplifying this particular example, I'd like to change this to say from 0K to degrees Celsius, because this is the conversion that we will use most often in this class, is going between Kelvin and Celsius. So the thing you need to remember is that a Kelvin temperature is equal to the Celsius temperature plus 273, which intuitively should mean that to go the other direction, Kelvin minus 273 would be equal to the Celsius temperature. So if we have 0 Kelvin, if you subtract 273, that will give you your Celsius temperature, which here would be negative 273. And having a negative Celsius temperature is possible. As a reminder, if you want to remember how to convert between temperature units of Fahrenheit, degrees Celsius is equal to 5/9 the Fahrenheit temperature minus 32. And you can do a little algebra to go back and forth with that one. The next question says, which way will heat be transferred? This was one we talked about a lot. And just generally speaking, heat is always going to transfer from the hotter object towards the colder one. So we always go from hot to cold until we reach that thermal equilibrium. And then lastly, what is the difference between heat and temperature? Temperature, if you recall, is how we define the average kinetic energy of the molecules in the sample. There's no way for us to actually measure the speed or the motion of the molecules, but if we measure the temperature, that gives us a correlation. So temperature is how we measure how quickly molecules are moving. The faster they're moving, the higher the temperature. Whereas heat is the total amount of energy. So temperature only deals with the kinetic energy of speed of a particular set of molecules, whereas heat is talking about all of the energy, not just the kinetic energy, but also the potential energy stored in a sample. So now we can do a little math. When we're talking about specific heat capacity, we use this Q equals mCp delta T, where delta T is always the final temperature minus the initial temperature. So the first question says, what is the mass of copper when the temperature increases by 5 degrees if it's subjected to 2.8 times 10 to the 8th joules of energy? So our Q here is given to us. The energy is 2.8 times 10 to the 8th power. We're also told what our delta T is. It says it changes by a factor of 5 degrees. The question doesn't specifically tell us what the specific heat is. However, you have a large table over here that does have specific heat of copper listed. So we know that value to be 3.8 times 10 to the 2nd power, and we are going to solve for our mass term. So if you just substitute everything in to the little Q equals MCAT formula, we get 2.8 times 10 to the 8th power is equal to our unknown, which is mass, times the specific heat, times the change in temperature. And once you solve all that out, I find that the mass of this object is a really huge number. Grams, and if we're going to be picky about significant figures, which you should always try, the smallest number of sig figs here was 5. So the number 5, which means we have 1 sig fig, so this number rounded to 1 sig fig is just 1 with 5 placeholders. 3, 4, 5. So that is 100,000 grams would be your sig fig answer. The next one says we have a 250 gram sample of ethyl alcohol, and it's initially at 10 degrees Celsius and subjected to 20,000 joules. What is the final temperature? So here we know the mass to be 250. We know this is ethyl alcohol, so we can check our specific heat over in that table. And that guy is 2.46 times 10 to the third power. Tells me the Q is 20,000 joules and that the initial temperature is 10 degrees Celsius and our final temperature is the thing we don't know. So we can go ahead and plug some stuff into our little Q equals MCAT equation. So we find that 20,000 joules of energy is equal to the mass, which was 250, times the specific heat, 2.46 times 10 to the third power, times delta T, which if you remember is temperature final minus temperature initial. So we don't know the final temperature, so that's like our X, minus the initial temperature, which was 10 degrees Celsius. It is important that you double check to make sure that the units of your specific heat match the units that you're using to do all of your math. So up here, if we check the units of our specific heat, the unit of temperature is in degrees Celsius, which means this temperature unit is okay for me to use. If it was in Kelvin, I would have to change that. The unit of energy is in joules, so this is good. And the unit of mass here is in kilograms, which means I need to convert this mass to kilograms so that my decimal ends up in the correct place when I'm all said and done, which unfortunately I forgot to do up here, which means this answer is actually in kilograms, not grams. So before I start, I'm going to go ahead and do that. So there are 1,000 grams in 1 kilogram. So that just means I got to divide this number by 1,000 or move my decimal 3 places to the left to give me kilograms. So there we go. So when we start working all this out, we got 20,000 equals 615 times x minus 10. And so you distribute here. We get 20,000 equals 615x minus 6150. Combine your like terms. So sounds like 26,550 is equal to 615 minus times x, and then divide by 615 on both sides, which I haven't done yet. And we get that x is equal to 42.52. We were solving for the final temperature, so this is going to be degrees Celsius. And again, checking for your sig figs. Looks like the smallest number of sig figs comes from this temperature measurement. So our final temperature must be in only 1 sig fig, which means this would be 40 degrees Celsius. Okay, lastly, which of the substances listed in the table would be the best insulator material and why? Meaning an insulator is slow to gain or lose heat, so we want something that has a really high specific heat. So in this case, water is the one in this table that has the highest specific heat, which means it's going to be very, very slow to change temperature. That's what the specific heat tells you. This guy's slow to change temperature. It requires a lot of energy to cause a temperature change. Last two questions. talking about enthalpy and defining things as endothermic and exothermic. So if delta H, which was that enthalpy term, which we spent just a little bit of time going over, and that's about as much energy as we need to put into it in this particular class. But if delta H is greater than 0, that means delta H is going to be a positive number. And if you have a positive number or a positive delta H, that is how we define an endothermic reaction, which means energy must flow out. Nope. Energy must flow into the system. So if you have a positive delta H, that means energy is going into the system. If you have a negative delta H, that is exothermic, which means energy is going out of the system. And then very last question for this video, describe endothermic and exothermic at both a molecular and macroscopic level. So macroscopic's easy. We've actually already done this. Macroscopic says that energy flows from the hot to the cold. So energy always goes from the hot to the cold. So let's say that your system was the cold thing. If your system is the cold thing and energy is flowing into the system, then this is our endothermic reaction. If our system is the hot thing, then energy is flowing out of the system, which would be an exothermic process. Then if we think about this on the molecular level, the hot molecules are moving really, really quickly. So if they're colliding with slower moving molecules, they are transferring their energy out of the hot thing into the cold thing until we get to thermal equilibrium. So if your system is the cold thing, it is absorbing that kinetic energy so that it will speed up, and then the surroundings are going to slow down. So that is endothermic. If your system is the hot thing, then it is slowing down because it's transferring its energy, it's losing energy to the surroundings, and so that would be our exothermic process. Please make sure you take time to complete the independent practice, come in for test corrections, and then you can retake the test when you're ready. Thank you.